Thank you for coming to the talk. I know it's sort of late in the day, and it's a bit of an endurance is sitting in front of all these talks and trying to keep your focus so you're bringing it all in. This should be a fairly easy talk. This isn't a product sell. This isn't a we've got the best technology. This is more of a philosophical talk, evangelizing maybe a particular way ahead, okay? And so, if you have any questions or opinions, please feel free to stop me. So I work for IBM in Almaden. I've only been there a year, which is very small in terms of IBM terms. The guys up there we've just got one guy that's reached 50 years. So I'm like, holy crap. So yeah, I used to work for Samsung, Lockheed Martin, and Bell Labs before that. So I've done sort of the whole set of industries, defense, consumer, business. But predominantly I've looked at how you align the software to the changing hardware, and particularly how you really get the best performance out of the hardware. Okay? So what I'm going to talk about today is really, I'm trying to get a message across, I guess, on two parts. The first is we really need to do something about the way we engineer our I/O stacks. The hardware is moving so fast, so much further in front of the software. The software is now the new problem. So that's my first position. My second position is we need to be able to develop our I/O stacks and make them more flexible so that we can meet specific application requirements. So, for instance, in here, how many people have implemented their own file system? Okay, a couple, that's good. But typically, not so many, because engineering a file system is complex, particularly when a lot of the work is in the kernel. It's quite a hill to climb. But my philosophy is, really we need to start thinking about compositional I/O, and we need to think about providing building blocks so that we can actually build our own I/O stacks for our particular application needs. Okay, so let's move forward. Some disclaimer blurb. So let's first think about what's happening just quickly from the hardware perspective. And I know you guys will have seen this slide or similar slides a million times before, but really in the last few years, we've seen an advent of something newer than flash, and that's what you might term storage class memories. We're seeing now Optane 3D Crosspoint, i.e. Optane and Apache Pass, being the first real incarnation of something different from NAND flash. And then we're seeing these other things coming down the technology pipeline. This talk's competing with the persistent memory talk. Everyone's excited about persistent memory. There's persistence on the memory bus. It's going to be fantastic. So there's even faster technologies coming along. So what I want to do is try and give you a better sense of, okay, what do the performance envelopes for these technologies actually look like, rather than, okay, it's just Optane, it's faster, blah, blah, blah. And I'm IBM, so I don't really care whether it's 3D Crosspoint or something else, but it just happens that 3D Crosspoint is what we can get today. So just to clarify, 3D Crosspoint is a very different media technology. It's PCM-like, phase change memory-like. One of the biggest differences is that the firmware is much simpler. So the consequence of that is more stable latency. So there's no need to do large block erasers. There's no need to do wear leveling as much. It's got much simpler firmware. I can only tell you that because Intel, of course, are keeping it close to their own chests. There are two versions of 3D Crosspoint, one of which is generally available. That's Optane. So that's the P4800. That's an NVMe form factor card. And then there's Apache Pass, which is the NVDIMM version, which we expect to see, best case, again, this is my opinion, not a company statement from Intel, or best case, I think, next year. I think we'll start to get, it'll be the end of next year, we'll start to get engineering product samples this year, and really, of course, the changes have been made in the the Perley architecture with a hybrid memory controller, because you need a synchronous and asynchronous memory controller to put a 3D crosspoint in the box. Those changes to the microarchitecture Intel have done. The stopping block, I guess, is probably connected with heat, but we don't know what's sort of causing the delay on the release of that. But we do expect it to come out soon. And so Apache Pass will be 3D crosspoint on the memory bus. People say, well, it's byte addressable. Well, it's not really byte addressable because you're still going to use cache lines, so it's more likely to be cache line addressable, even though in theory you can address individual bytes. So that's 3D crosspoint, and really that represents what we have today that fits under this umbrella of storage class memories. This is a technology that basically is breaking the 10 microsecond boundary. So let me show you some results to give you a better sense of what the performance of one of these devices looks like. So on the far left-hand side, so this data is from SPDK and actually UMVMe. So this is best case scenario for these devices. This is basically taking the software out of the picture and just putting things in the queue, submission queues and completion queues and doing polling on that. So this is pretty much as much you will get out of a single device. Okay. The biggest thing to note is there's a lot more symmetry on the read and write throughput, which is very different from many of the NAND flash products. You will see a much lower write rate on the NAND flash products. The other noticeable thing here is, as I mentioned before, an order of magnitude more stability in the latency. So here, I'm just looking at the presentation mode. It's like really small, and I can't quite see that around there. You can see that the worst case latency for this is a sustained run by weight. This is running over hours. This isn't running for 10 minutes. So we've really pushed the device and made sure that it's not clean anymore. But the worst case latency for these Optane devices coming out at about 50 microseconds. Typical latency that I'm seeing is in the order of 8 microseconds, read and write symmetric again. Okay, so this is considerably faster than NAND flash, and that worst case scenario, either long tail, is much smaller. I mean, in NAND flash, you can quite happily see thousands of microseconds. Okay, remember these are microseconds, not milliseconds. So these devices are kick-ass fast, in my opinion. I mean, it's just unbelievable, really, if you try and get your head around what's actually going on. So that's what Optane numbers look like. That's real data collected in the lab. I'm IBM, I'm not Intel, I'm not Micron, so they're honest numbers. They're not being fiddled with. Not that I would suggest they would do such a thing. Okay, and there are, of course, other technologies coming down the pipeline. So Micron were part of the development of 3D Crosspoint, so they're trying to market this under the Quantex brand. And we expect to see similar behavior of performance characteristics to the Optane devices from Micron. Although actually it says there that they're looking at 1.8 million IOPS, so they're actually trying to push. So the IOP boundary for Optane is currently about 600K IOPS. So these guys, Micron, are looking at actually increasing that probably for the read workload. And then we have, to make sure nobody's left out, Samsung have their own new type of NVMe device which is aimed at low latency. This is the Z-NAND device. This is an SLC device. It basically uses the same fundamental NAND flash structure but a different arrangement of the controller. And this is available today, which I found out recently. And you can expect in the order of magnitude of 12 to 20 microseconds read and 16 microseconds write, with 30 drive writes per day.
You don't want to queue that loss for that?
No, I don't. That's their data. That's not my data. That's a good point, actually. Very good point. The previous slide was my data. This slide is marketing data. So I'm actually soon to get some of these devices in the lab and repeat the exercise and actually find out what the performance looks like. Good question, though. Okay, but again, you know, these are fast devices. We're talking sort of less than 20 microseconds. That's not a lot of time. And then just to make sure that we've all sort of caught up with the technology trend in the network side of things, I wanted to show you this chart. The network devices are also getting, at least the local area network devices are getting kick-ass fast. I mean, now we've got Mellanox releasing 200 gigabit Ethernet. We're pushing over 100 million packets per second. These are extremely fast network cards. My brain can't get around the idea of shifting 100 million frames in a second. It's just, to me, it's just amazing. But of course, we can't do anything about the speed of light, and long haul is likely to remain a problem. It's not going away anytime soon. The routers are different, the arrangement's different, the QoS is different, and the speed of light is the speed of light. So really this technology doesn't really do much for the internet per se, but it does do a lot for the data centers and the local area networks, of course. But I just wanted to give you that number again to sort of try and put some perspective on how fast are these things actually today. Okay, so I did a little bit of history digging myself and sort of was trying to understand what was happening. And I actually did the data collection of looking how performance, or relative performance, has changed for storage, network, and compute over the last 30 years. And of course, we all know about Moore's law, et cetera, et cetera. But something that's interesting that came out of this, collecting this data, again, this is my data, so I'm to blame if it's wrong, is that, of course, we know that the CPU performance is sort of flattened out, or what we've done is we've transitioned from increasing clock frequency to adding more cores. But the problem now is we're sort of getting to the point of, well, there's only so many things we could do with so many cores. So actually we're seeing a flattening of the compute curve. And meanwhile, the network thing has sort of just continued at about the same rate of progress, but we're seeing an uptick on the storage performance. And that uptick is pretty much caused by NAND flash and now the future of the successor to NAND flash, i.e. Optane or 3D XPoint and other SCM technologies. Okay, so the point here of this chart is you'll notice that we're on an uptick for storage and we're on a downtick for CPU. Okay. So what does that mean? Well, again, thinking about the performance of these devices. So back in 2010, the world was easy for us software developers. We had, for a single, at 40,000 or 40,000 IOPS per second, 4K, we had approximately 172 microseconds latency for the device. Great, loads of time. That's quite a few cycles. That's hundreds of thousands of clock cycles. Plenty of time to mess around in the software, plenty of time to go through abstractions, plenty of time to locate that block or do whatever we want. And so a software latency here, I've used the example of ext2 implementation from Linux, which comes out at about 12 microseconds. Here you can see in 2010, the software is not the bottleneck. Waiting for the I/O is the bottleneck. But now if we spin forward to 2017 and we start thinking about these fast NVMe devices, and let's say we're looking at Optane and we've got in the order of 7 microseconds, suddenly we're spending more time in the software than in the hardware. And in fact, the wall clock time is about 17,000 clock cycles. So that isn't a lot of time. Now, of course, we can still do pipelining, and we can hide latency effects, but there's a limit to how much pipelining we can do as well. And if we really want to, I mean, that does raise an interesting question is, even if you don't want latency, low latency, sorry, then why bother investing in Optane in the first place, or some of this expensive SCM technology? If you're going to do pipelining, you might as well use NAND flash. That's what it comes down to, which is much cheaper technology. But if you're building something like a high-frequency trading system where you can't hide the latency through pipelining, then the software really becomes the problem. And so my position is, if you're not willing to take care of your software, then you might as well not buy that fancy low latency device. It's a waste of money. Okay? And the problem's going to get worse when we look at NVDIMM. Because, of course, NVDIMM will be probably an order of magnitude faster than these devices that sat on the PCI Express bus. So again, if we're not willing to take notice of the software piece and notice of the overhead of the software, then there's really no point in justifying the cost for those devices. Okay. So just to give you another perspective on the software overhead, this is some more data that I collected from the Optane device, QDepth1 and QDepth32. Again, on the left-hand side, we sort of see raw performance. That's data collected through SPDK. I'm assuming you all know what SPDK is. It's basically the user-level device driver framework that Intel started and that's now in the Linux Foundation. Basically, it represents the best you're going to get in terms of software, reducing software overhead for the device. Okay, we'll talk a little bit more about that shortly. And you'll see that what basically happens is, as we add the file system, the curve sort of dropped down. Now, also what I need to point out here is actually the kernel driver. So if you look at the kernel driver in the middle and we go, okay, 5 threads, that's about a gigabyte per second. Well, actually, remember, that's user-level threads. The kernel driver, of course, makes I/O threads for every core on the system. And so this data, I should have really, in afterthought, I should have really limited the number of I/O threads being created by the kernel driver. But so when you see here, for the kernel driver, for instance, here is, this is sort of doing better than this. It's because that kernel driver is actually spinning up kernel I/O threads to do the work, and then we've got 1 or 2 or 5 user-level threads that are passing work down to those kernel threads. So it's a little bit deceptive. That's the point here. That's using NVMe driver, correct? Yes, and that's using the new NVMe driver, the multi-queue NVMe driver. But there is actually a way you can limit how many queues it creates and how many threads, and I didn't do that, and I should have done that really. But I didn't realize what was happening until after, and I was like, oh, right, yeah. Now, of course, also the other thing here is, if you want throughput, you need parallelism. You get parallelism through queue depth or threads, CPU threads, okay, or a mixture of the two. So that's worth bearing in mind. Now, so now this is some data that I collected from Linux again. This time ext4. Actually, ext4 seems to do a bit better than ext2 in some circumstances, but let's not get into that. This was data collected from a Samsung reference box, flash JBOF box, with 24 NVMe devices. And what I did is some basic FIO testing on that. Now, this performance data is not the consequence of anything to do with Samsung's box. Samsung's box is great. It does what it's supposed to do. But what you'll see here is actually ext4 starts scaling brilliantly. And actually, we can get up into the region of about 3.5 million IOPS, just under 3.2 million IOPS per second through ext. Now, but bear in mind, there's no file sharing here or lock contention. It's fairly straightforward access, okay? But actually, that's better than I expected it to be. But then after we get past 3.2, it sort of flattens off, and then it falls apart. And I also want to point out the dotted line here, which is the total CPU load. This is critical, okay? It's not so much that some of these existing operating system technologies don't scale, it's that these existing operating system technology and I/O stacks and file systems demand heavy use of the CPU to do I/O. That's the point, okay? That's the problem we have. We're having to now spend all of our CPU power, cycles, to actually process the I/O. And we've seen it in our own products where we've put these high-performance devices in, and we can't saturate the performance of the devices because of the software overhead in conventional file system designs. Okay, so here shows you the situation with this box that, okay, with AXT4, I can get to about half of the performance, the theoretical performance of that 24 devices, because the theoretical performance is, I haven't got it on the slide, is 6.5 million IOPS, so I can get halfway there, but at a cost of 30% of the CPU. That's quite a lot of CPU I'm burning just doing I/O. So this is my justification why we need to really start rethinking how we design the operating system and how we design I/O and file systems and so forth. Sorry? This isn't using a single core. This is using, it's a 48-core server, E5 26699, the number of threads on the bottom. Now, it doesn't fall, this is a good question as well, actually. The drop-off here could be to do with hyperthreading, actually. That's why the erratic behavior, and not the drop-off, but the erratic behavior is starting to kick in. Okay, so this is on a 48, I think it's 48-core server. So, you know, you've put 24 devices in this box, you can't really unleash the performance, that's the point. You know, it's very difficult with a standard stack. So what vendors are doing now, of course, we're seeing this, is I put these in a box and I put some high-performance Mellanox cards on it, and then I can distribute it to more machines, and that's how I can use the capacity available in the box. But that...
48 queues?
Yeah.
48 cores?
Yeah.
And the bottleneck is in the stack?
Correct. Yes.
Is this just reads?
This is writes, actually. Random writes. Yeah, I made some notes here because I forgot to put it on the chart, and I was like, shit. Yeah, it's random writes, actually.
So do you know what the write-up of the drive is over time? Is it reached a steady state?
I don't know that. But this was run over a long period of time. This was not a quick run. You know, this was multi-hours of running. But I don't know what the state of the drives were. Yeah.
It's always been a difficulty we've had with random writes.
Yeah.
Especially at lower queue depth, it can be deceiving because the drive can actually catch up. It has bandwidth to kind of get ahead and be able to mask that for a period of time.
Yeah, exactly. And that's why you've got to push it and keep pushing it for a long time to really get it to steady state. Yeah. I'm hoping that I've got rid of any hiding of problems. Okay. All right, we wanted also to talk about context. So we've talked about these devices, we've talked about, you know, orders of sub 10 microseconds, and we've worked out that that's sort of about 20,000 wall clock cycles per I/O. And so let's just quickly talk about context switch overheads. Now, remember that a system call is not a context switch. A system call is a system call, and it's much faster than a context switch. But the problem is many of these device drivers set up threads per core and hence incur a context switch. And context switches are typically, at best case, about 1,000 cycles. But depending on the working set size and how much you trash the cache in doing so I've done the context switch in, the new task that I've switched in, if it then destroys the cache, of course, doing the next context switch back is going to be much more expensive. And this shows you here how, as you increase there was a paper some time ago that had very similar data, but I thought I would recollect it with modern hardware because the paper was done sort of maybe 10 years ago. But they're very similar, not much has really changed. And so as you increase the working set size, you can see that the context switch latency can easily exceed 1,000 microseconds. So again, you know,
Bare metal? Is that
bare metal.
bare metal?
Bare metal. Oh yeah,
Virtualized.
not virtualized. No, I'm sure it'd be a lot worse virtualized. Well, the VT entry and exit would be bad. So again, you know, you've got to be so careful because you can do these micro benchmarks which aren't carrying a working set size and not trashing the cache, and you go, hey, wow, this isn't too bad, this context switch cost. Oh, well, it can be. So, you know, you have to sort of keep your eye on that. My belief is context switching is pretty bad. We need to avoid it. And one of the ways to do that is move things into the user space, which we'll talk about. Now, and again, you know, I'm sure you've all heard the talks around SPDK and things like this, but I wanted to sort of just, again, take a sort of philosophical view and think about, sorry.
Add one more.
Oh.
On the previous slide. So the context switch, is that due to interrupts mostly? The penalty play was that due to the interrupts. Context switch.
Yes, but it's not the interrupt is the big penalty because the interrupt cost wouldn't change.
I was wondering if you correlate the interrupts.
Yeah, the problem is the cache effects on bringing the program state back and filling the registers back in and out.
Warming up the cache.
Yes, or basically polluting the cache. That's what the working set's doing. It's polluting the cache. So I think the interrupt cost is sort of fixed, and that's not too bad, I don't think, because a system call would do that. Yeah, I'm not sure. I'm not sure we can talk about that.
But it helps in the virtualized case. When you virtualize it, it collates that. Yeah.
Okay. Point is, context switching is bad. And you know, of course, there's been optimizations at the microprocessor level to try and optimize context switching, but I don't think there's much they can do. I mean, not sure why, for instance, they don't have some special, maybe they will with the new cache management, so you can partition the cache and say, this is for task contexts, and don't touch it, you know. Maybe there are solutions to that, workarounds. Okay, so now we're going to talk about user level or rethinking, and there are two things that I mentioned at the start of the talk, and that's user level I/O and then tailoring I/O. So user level I/O, for those who aren't entirely familiar, is this notion of bringing both the control and data plane into user space. So I'm not basically running any code in kernel or in ring 0 privilege for Intel. And the thing that enabled this, because, you know, we've talked about this for years. I've done quite a lot of work in the microkernel community, okay? The microkernel ethos is, of course, put everything in user space, just about. But for a long time, it wasn't viable because by putting things in the user space, we had this problem of you could basically do DMA to anywhere. And so you lost all your privilege protection and your stability of your system. So the thing that changed the game is the IOMMU. That allows us to establish a user-level process and give it a particular area of memory, DMAable, on a device, and limit it to that. So we can stop these user-level device drivers basically accessing any memory. That wouldn't work. But now today with IOMMUs, we can enable user-level device drivers, and furthermore, we can even have user-level device drivers running at ring 3, i.e. user mode, not kernel mode, not root mode or kernel mode, and they can still do their job in interacting with the device. You know, we can use the kernel to sort of do some of the management stuff, but the top and bottom of it is we can now build user-level device drivers, we can run them as non-root, non-privileged processors, and we can avoid going into the kernel altogether. Now, so why hasn't this happened? Well, I think it's beginning to happen. And the network community jumped on this years ago because the network community, you know, they invented 50 gig gigabit Ethernet cards, and they said, well, there's no way we can go through the kernel. And then so what they started to do is move it into user space. And now what's happening is that the storage guys, IOs, are all moving in that same direction. If you want to get rid of the kernel, you want to get rid of the context switches, you want to have better control of cache, threading, etc., you need to put it into user space. That's at least my position. There's an interesting side effect of this, at least in the Linux community, of course, is the licensing. So now if you do this and you build your I/O system in user space, you're subject to LGPL, not to GPL, and thus you can keep your intellectual property, you can keep your source code close. Of course, the kernel developers hate this idea because it's relinquishing some of their ivory tower, as it were. It's relinquishing some of their domain. You're suddenly starting to put what they used to have to do in the kernel into user space. Now, the second point here that to me is most important is by putting it into user space, we're also enabling more flexible programming. We can use pretty much any programming language we want. Okay, you're not going to start writing file systems in Python. Well, some people have, but it's not ideal, but you could do it. You've opened up this world of file system development, of block driver development, of encryption, of security, of distribution to the average programmer. They can use their tools that they normally use. There's no real hurdle to doing that. And if we can do that, then we can move to this idea of, well, now people can start composing their I/O stacks. They can start customizing their I/O to what the application actually needs. And that's what I believe ultimately needs to happen. But, of course, in a system where you're trying to support lots of workloads, this probably isn't going to work. So I'm more thinking from the direction of thinking about a system that's more appliance-based. You know, it's a database, it's got one particular workload. And you'll see actually this technique, we have heard talks today that have echoed some of these sentiments. We've got the Ceph guys who use it, replace their back end with their own file system that's optimized for what they need. I'm 100% in belief that's the way ahead. Okay. And so we don't really need to say this, but we'll skip this slide. But basically this says, look, by doing so, we can dramatically reduce latency, we can dramatically bring that upper bound down, we can really get much better performance. And this performance gap is only going to get bigger as these devices, the hardware devices, get bigger, because the CPUs aren't getting faster anytime soon. So we'll get more cores, but that again, actually user-level device drivers, I should just quickly mention that. Let me just check. Yeah, of course, user-level device drivers don't handle interrupts directly. So that's another thing that sort of changed, is the hardware devices suddenly don't do something like generating an interrupt per packet. What they do is generate an interrupt, atomically mask it, you service the queue, and when the queue is empty, then you can clear the interrupt and continue. So if you reduce the interrupt load. Now, in Intel, you can't, at least to my knowledge, you can't handle the interrupts in user space because the code, the vectors need to be executed in privilege ring 0. So you can't really handle those in user space. You still have to put them through the kernel.
If you do pass-through, you do that. But you need BIOS support.
Sure. Yeah, that's too fancy. Okay, so we're seeing some emerging ecosystems around this notion of user-level user-level device drivers and user-level system code development. Maybe one of the starting ones was DPDK, which was set off by Intel to support their high-performance networking cards. And then they sort of followed on with SPDK, which used DPDK and so forth. But there are others here, including my own work, which is not announced yet, but hopefully will be by the end of this year. But there's lots of work on this idea of really using user-level customized data planes to improve performance. DPDK, we won't go into a huge amount of detail, but what does it really provide you? Actually, it uses VFIO, which is the device driver Yes, it is a device driver, but you only need to use it for sort of establishing the control. But it allows you to, for instance, probe the PCI express bus and bring the PCI registers accessible into user space. That's basically what it does. But VFIO, its predecessor UIO, did the same thing, but VFIO uses the IOMMU. So really, it's the only way to do it if you want any protection. Okay, so they use VFIO at the bottom, and then they layer on things like lock-free queues and various strategies for polling the devices, and all the NVMe register standards and so forth. And then they've started adding in SPDK more layers of capabilities such as RDMA targets and hosts and so forth. Okay, so it's a big code base that's growing and sort of provides you with a smorgasbord of libraries and APIs to get going. I did want to talk about, we mentioned this briefly. So interrupts aren't delivered to user space. So the big change is these device drivers are basically polling. So we have to have a thread that's polling the device, and it's busy waiting. Okay. The consequence of that is, well, actually, it's not too bad because we've got lots of cores typically. However, we have to be a little bit careful because, for instance, we don't want to set up one polling thread per queue, per hardware queue, or even per device maybe. If you've got lots of devices, you're going to again run out of CPUs. So if you do go into this world and you start building this software and you're wondering, sort of thinking about how to do it, the design pattern is basically asynchronous task polling. What you're doing is you're setting one thread which is round-robin, servicing queues and servicing completions and pushing the next thing on and servicing more than one device. Okay, so you've got to be careful not to tie one thread up with one queue because then you'll be in a situation where you've no CPU left anyway. Okay, and of course you want to use lock-free because in all this communication and all this servicing of queues and things that you're doing, you don't want to drop into the kernel at any point. If you do a system call or a kernel call, you're sort of done. So everything has to be in user space. So you can't go to sleep. There's no pthread mutex uses or fast mutexes. You need to start using spin locks, and you need to start using lock-free data structures. That's the top and bottom of it. But if you do that, then you should be able to, for instance, with one thread, I've worked out with some experimental data that you should be able to service an NVMe device at around, or N NVMe devices, up to about 5 million IOPS on a single core. So if you do it right, there's a huge gain to be had, because if I can do 5 million IOPS on a single core, and I'm in a server system and I've got 47 cores left or more, then I've got more CPU to do useful things like erasure coding and so forth. Okay. Some of the key challenges: integration with POSIX. That's a challenge, legacy integration. There has been some work in this, I can't remember the name of the university, but a European university that had this approach of basically an I/O interceptor. It's fairly straightforward. You basically use a sort of LD preload type thing, and you intercept the system calls specific to that device. So you sort of, you're catching your open and your reads and write calls, and you're sort of redirecting them to your user space if you can. And if they go to the normal device, then they'll drop into the kernel. But you basically intercept the system call mechanism to redirect it to your user level stack. With that LD preload, they just basically overload the symbols in the runtime. Yeah. So it's fairly easy, actually. I mean, I think it becomes sort of tricky when you've got POSIX calls that are fairly complex that you can't easily track or support in your user level thing, because most of the time you're going to have a user level stack that's maybe not quite as capable as, let's say, a full POSIX compliant file system. Protecting sharing of storage devices, with NVMe SRIOV is coming out, which of course is the single root I/O virtualization. Basically allows you to virtualize the NVMe devices. So that sort of fits some of that problem. Memory flush. So if I've got, you know, a piece of memory, one of the issues, and I'm backing that memory with, so let's say it's DRAM backed with NVMe. One of the issues is, okay, if I modify that memory, in that DRAM, how do I know which parts to flush to NVMe? And conventionally, the kernel, of course, uses the page table to do that. But we can't use the page table because we don't really want to go into the kernel. You could maybe go into the kernel every now and then and collect some data and then do the flush. I have done work around sort of collecting a dirty bitmap and then bringing it back to user space and pushing it through. But it's not ideal. And in fact, in some cases, even just doing a checksum is more effective than going into the kernel, doing the tree traversal, finding out the dirty pages, coming back out, and then saying, okay, these are the pages that I need to flush through from DRAM to NVMe. But doing a simple checksum on those is actually, in some occasions, faster. Another issue is memory paging and swapping. How do you do user-level page fault handling? If I want an extended memory model, let's say I'm using a small amount of DRAM backed with NVMe, how do I actually do that without going into the kernel? Again, the problem is with Intel is that the exception handling has to be in ring 0, so you can't really do that in user level. You could use something like Dune, which uses virtualization. I've tried it. It costs too much. The VM exit and VM enter basically cost too much. The last solution that I have in place in my own work is actually just using mprotect and mmap. And I've actually managed to get the paging down to exactly the same as the kernel. By doing, so what happens is you get a page fault, and then a signal happens up to the application. The application does the user level paging with direct I/O through the SBDK, and then drops back down. And I've actually managed to get that to about the same as kernel paging. So it is sort of doable, but it's a little bit tricky. Okay, I'm going to just quickly speed up now because I've not too many slides left, but we're nearly out of time. Okay, and then so also we need to start thinking as all these NVDIMM devices come along. Now we've got devices on the memory bus. Of course, we can consume them as the storage paradigm, but we probably want to consume them as memory. We probably want to use the same data structures that we use for programming in DRAM to represent data in this persistent memory. And this is where all the PMEM-IO stuff is coming in. There are various challenges. So don't think that when you get this persistent memory, you're going to take all your existing data structures and put them on it. Because I can tell you now from experience, you're not going to be able to do that. So for instance, the standard libraries, STL libraries, let's say you take something like a hash map. That is not easy to put on persistent memory because the data structure itself embeds allocator, dynamic memory allocator information in the data structure. And so and that's code. So you can reload the data into the same part of virtual memory, but you can't then make sure that the code's in the same part of memory, and thus the data structure sort of falls apart. So there are some nuances about putting data structures, existing data types, in persistent memory. It isn't that easy, although it can be done. I actually ended up using STL from EA Games, which is a modification of STL that allows you to more explicitly overwrite the allocators, and therefore when you reload it, you can override the allocator and it will behave nicely. So, but the point is I'm trying to get across here is, even though you might have persistent memory, it's non-trivial to actually use it. There's some legwork to do to actually use it. There was a lot of work done back in the 80s and 90s around programming language support for persistence. They had this notion of orthogonal persistence, where you sort of got transparent persistence across all data types. And then there's more recent work around sort of heterogeneous heap management, because that's what you really need. The expectation is you're not going to take your software and put it all in DRAM or all in persistent memory. You're going to split it. You're going to have some data structures in persistent memory, some data structures in DRAM, and you've got to get the two to behave. You don't want pointers across the two. That's what we call heap pollution. So you need to avoid heap pollution to actually be able to use this persistent memory. All right, sorry I haven't got more time to go into this. Yeah, we've talked about most of these anyway. Oh, yeah, last point is, and also I'd like you to sort of think about, you know, let's say we have these NVDIMMs and we have this user level stack type thing. How do we do things like layering services and actually, because we've lost the interception point. So let's say I want to make sure that an application only writes to some specific area of NV memory. How do I do that? I don't know how to do that. I think that's a question that remains. You know, because in a storage system, we've got a gateway. You know, we issue commands to the device and the device goes, yeah, that makes sense, I can do that. And we can have device drivers which layer on things like logical volumes and protection and boundaries. We don't have that with NVDIMM, and so that raises the question of how do we layer these services on? Possibly. Yeah, possibly. It's a tricky problem. And that might be it. We might need to see changes in the microarchitecture, further changes in the microarchitecture to answer some of these questions. And I actually believe as well with polling, for instance, if we do move to this busy waiting polling-based systems, then it probably would be useful to have some little cores. You know, we have this big little core thing. Some little cores at lower frequency that have got very shallow pipelines that are just polling registers. So we just need a microprocessor vendor to take notice. IBM. All right. Okay, so to wrap up, so I'm going to get hoisted here. CPU is the new scarce resource. That's the number one takeaway. And kernel bypass helps with this. Eliminate system calls and, oh, actually I haven't written it here, and context switches more importantly. But I think the real power is going to come where we can ease the development of tailored I/O stacks, and we can start sort of making it simpler for developers to construct what they need for their I/O purposes. You know, instead of having a file system that does journaling because it does, if I don't need crash consistency, why am I paying for it? So that's the idea. But of course, there are lots of challenges, and tools, and things. And then the final slide, recommended reading. If you've not seen this article from Luis Barrazo and Dave Patterson, etc., this is quite an interesting article that came out in ACM Communications recently. And it basically talks about this void that we have in terms of we can deal with very nanosecond level things, we can deal with millisecond level things, but we're not very good at dealing with microsecond level things. And so what I've talked about sort of disconnects with that. And that's it. That's all I have.